Well, after the fresh disappointment I had with the previous projects I have tried to do, it was a book recorder, and I thought it would be simple to actually get through this, but I felt very weak on my front end skills that almost vanished. Using Tailwind CSS, not being able to rescale um, the divisions on my flex boxes. So I felt like really desolated. So I thought like of going through a simpler project would be a better idea, where I could be using as well, using the web dictaphone here, and as an example of how to get there as a tutorial. But this will be like really vanilla JavaScript and will have better used um, another approach. And I think I could be able to get there, but too many disappointments over there. So I have a very idea I want to share about a game I could be making uh, for um, for taking my time. But I think it's also a good time to find also which game engine we would like to be using here. Um, so I think that JavaScript is a good language to write a game. We can write a game inside of Canvas. I think Canvas can really work here, and with solidjs we could. I don't know if there is. We need some proof of concept of the game, something that will be very simple. So for the UI, how that we will be able to create this game. But first, maybe it's a good idea to get an idea of how the game would behave, and what are exactly the principle of the game. All right, so let's say we are inside a canvas, which is the game canvas, and that we would have like a little object with a given mass, so and a given energy, depending of its velocity, and we'll have the norm two of its velocity. And the norm 2 will be also squared. Um, so that will be the idea of the game, and that will be a multiplayer game. And the way between the only thing is that so we can have the to bound the some keys for moving in the game. And then we can have another um, canvas that control another player, and we'll be using nats for the players to connect together in the game. So this is about the idea, or like the concept I would like to implement. I don't know how hard it is. So, and then of course, like things like what happen if we have a little crash. So if two vehicles are going into a crash, then they will both get penalty from uh, the collision. And so, as they will get penalties from their collision, um, it will be necessary to create some algorithm for making two cars getting in a collision, and how you actually detect that two cars have been colliding. So we have a point here. We have another point here. And we can see that when you have two rectangles, they actually define limits that cannot be crossed by another point. So here we have a cross. So we can be always computing the differences between the points that shouldn't overlaps and see when we have a positive or negative impact. And we have to do this for all the objects. So this collision algorithm will be server side. And when they have a collision, um, depending on the energy, so we'll have a car that have a certain speed here and another car that have another speed here. We can try a different way to impact the game first. So the first way we could design, we can say if the first car have a greatest impact, greater velocity than the car. Let's name the car number 1, number 2. So if car number 1 has a greater than the car number 2, then we would like take car number 1 as the winner of the collision. But and in this case, we will have kind of equity issue, I guess. So what I found funny is that you find yourself the car cut by. All right, so I have to have a call. find it a bit more funnier if we actually are able to know. So, see, if again we have two rectangles colliding in some way, meaning that we can collect some points here, and if we have, so for example, this is also a colliding example, there is a collision here, we could take, so when we detect the collision, um, we could be uh, so how do we detect the collision here is that um, we could like, it's a condition between, so it has to be somehow that we are, so we have two sides, so this is a car, mm, at the limit. So I don't really know actually how you detect collision of two elements in a game. So collision rectangle algorithm could be just very easy. Rect. So indeed, it's pretty simple here, where everything is flat, right? So, but how do you do when it's not flat? So is there something about it? No, it's not the case. Can we circle collision? Because this one is easy. The one I'm trying to get is a bit more tricky, because like the rectangle are not flat like there is with angle. Collection detection between rotated rectangles. And this is already like a big video of 17 minutes. We could be watching this, or I prefer if we can find something. Basically, I have a bunch of rectangles floating around 8 different angles. Problems with reflection angles during collision resolution. Checking collision with rectangles at an angle. But it's true that we can like resume the problem to ordinary one rectangle that will be flat somewhere. Um, collision angle rectangle. but you can calculate where your point will be after rotation and use those points for collision. So we can um, we could like subscribe the rectangle in a circle and take this circle and make rotation between two circles first. And if we have colliding circles, then we can take a closer look, knowing that they are into uh, one circle. The problem here is that we need to have rectangles because the objects in the games would be rectangles. Or we could be using circles instead, and make the game even simpler just for proof of concepts with nats than to get blocked from the beginning with like a rectangle collision. A rectangular collision, because this problem here is not something that I see the solution anywhere easily. Can we maybe see if DeepSeek has a road for this? So I never used DeepSeek before. Uh, okay. There's an API platform. All right, I will be logging in first. So let's see. Um, Let me get a private email address first and generate a new password. this way. So to solve collision between two rectangles with different orientation, you can use the separating axis theorem. So it seems like the separated axis theorem. Oh man, there's so much. It's quite impressive. Instead of using a web research, if this is actually not hallucinating right now, it's my solution to my problem, and it's very bad because I wanted to find a solution for myself, and there's not anything to learn anymore, and the learning curve is going to get very fast steeper as hell. So maybe it's not like a good thing, but it's also a good thing because. So the set states that two convex shapes do not overlap if there exists a line along which the projections of the two shapes do not overlap. Indeed, um, indeed, if I go back to my little drawing here, if I'm able to, if there exists, so if there exists a line, so if for example here I need to so find this line first. So I don't know, for example, using this line here, I will find overlapping because I have one point where they overlap. It just has that this line goes through the point that is shared by the two rectangles. But it's also true if I draw also this line, because the projection will be this point here, and again this point will overlap also to this. So every line parallel to this line will also be a solution. So this is just an example, right? But the existence, where we say exists a line along which the parallel, the projections of the two shapes do not overlap. For rectangles, you only need to check the axes parallel to their edges. True. So axis parallel to their edges. So the edge of a rectangle would be the smaller, um, would be the smallest edge, or is it? Do I have to check all the lines there? So I'm not quite sure of what would be like the solution here. So there is, for example, one rectangle, and we have here. So we don't have to redo actually the full line. I could just draw another rectangle, and here I have two overlapping lines. Check the axis parallel to their edges. So this line, the first line I draw, would also be actually here, um, meaning that this point would be an overlapping point, but the distance to next rectangle is quite bigger. And to find the order in which these things are actually in is, I don't find a simple way to redraw what I've done, and is it true for all the possible axes. So let's try again. So I see two rectangles like this. Um, but also I would consider the closest one. So to find the closest one, like I would take this point and this point, and being able to find how much. So these are the closest points from each other's in the rectangle. So I could be computing these points, and once I get these points, um, these are the closest of the rectangles. So if they are the closest to the rectangles, we know that there, if there's a risk, it's actually there. Um, it's like if we had a circle in which the collision was possible. Next to the point in the middle, not really. So let's continue to read this interpretation. So for rectangles, you only need to check the axes parallel to their edges. Okay. Then we have steps to detect collision. A, define the rectangles. Rectangle A, center at x1, y1, wide at w1, height h1, rotation angle theta 1. Same thing for rectangle B. We just change everything with a little 2 instead of a little 1. Then we get the corners of each. Oh man, my microphone was muted all this time. And I was like complaining, like, why I don't have any sound there? So so there was a lot of drawing without any sound. Yeah, the microphone was cut for some time, so hopefully there were no viewers. Still, it is an interesting exercise to get through. Um, I'm trying to find some metrics, but let's just find first how they step to detect collision. So they define two rectangles, and we have a naming. So I guess there is some kind um, of to detect the angle. Would be how it cuts in here. So this will be the first angle, and for the first rectangle, and also for the second rectangle as well. Those are some angles, but like I will do a cleaner drawing here. So if we have a first rectangle doing this way, so this will be number 1. We have the center of the rectangle being located at x1 and y1. And there will be the height and the width of the rectangle, and there is place for a second rectangle that for the moment doesn't collide. So for this one, the angle I will not project it over there. I can just project it over here. So it's the second angle here. Then we have the center, x2, y2. We have divided the width and the height. We can compute the coordinate of the 4 corners of each rectangle using their centers, dimensions, and rotation angles. For example, for rectangle A. So corners of rectangle A or rectangle 1 would be to rotate local corners by the angle theta1 and move them by x1, y1. So meaning that we could take, I will duplicate this first. So we can take take local corners. So this one, then go with the wide, then height. Rotate it by θ2, and we'll get some rectangle that will be somewhere oops. So we'll be able to rotate this thing by theta, and it will just arrive already. Oops. Here we'll still have the width, the width here, and then the height here, and then we can still move this. So actually when you rotate it here, it will be instead be somewhere here. This is what it's supposed to be, somewhere like here. Like we only have to translate it afterwards. So this is the rotation. If you do it correctly, the rotation, it will end up here because it's rotated by a point here. I'm not sure about this. This step is not reliable yet. So if you apply the maths here and you do rotate, you will find that W12 minus H1 over 2. Okay, so those are local corners. So it's why the rectangle is being centered by theta. So it's actually not even this. It's more my green rectangle here with the local corners is centered around my origin. So it's somewhere there. Okay. So after that we have to find the axis to test. So for each rectangle, take the normals perpendicular vector to its edges. Since rectangles have parallel edges, you only need to test 2 axes per rectangle. Axis for rectangle A, U1 and U2, normal to its edges. And for rectangle B, V1 and V2, normal to its edges. So we have 2 edges per rectangle because they're parallel. And we have 2 vectors. We project the corner onto each axis. So for each axis, project the corners of both objects onto the axis. This gives you 2 interval, one for each rectangle on their axis. Oh, alright, interesting. Check of overlap. So in Python, for example, there is a get axis. There is a rectangle notion here, normalize, perpendicular, normalize, perp, edge, for edge and edges. There are optimization, and there is an example. Could you rewrite the pseudo code in golang? So we have a rectangle here, which is a structure. Center x, center y, width, height, rotation, type vector struct xy. I don't know where we actually need a vector. Well, we have the dot product for two vectors. We have perp. This is how you get the perp of a vector. We have normalize vector, very readable code. Normalize a vector. We got get corners. So get corners is for the local corners. Then we have rotated corners. And for I corner, range corners, rotated corners equals to vector of we move them by the center. Corner to x time cos minus corner dot y times sin, where sin is the sinus of rect rotation and the cos of rect rotation. So how much the corners are affected by the rotation. And this give us the rotated corners of a rectangle, where the rectangle is defined by its center, wide, height, and rotation. And finally, we project the rectangle corners. So we need multiple rectangles for each of range of all the other rectangles. It returns the min and max projection to an axis. So axis is the vector, and overlap would be two rectangle. We can test if they overlap this way. And rectangle collides will be to take two rectangles and that's a very nice and pretty sweet explanatory code. Like I can keep this one, or we can just rewrite it and comment a little more. Comment it a little more, but it's actually a very good code. And this is not anymore a problem. This is where we get to vibe coding style of code, which is crazy to think about, but is actually something that you can consider. DeepSeek has been pretty good for me for this one. I don't need pretty much more than this. So now that we know, so you actually get first the projection of your normal vectors. So if I get two rectangles here that does collide, we do find that the projection do actually overlaps here. This is what this function here get corners compute the corners of a rectangle. Get axis, project rectangle. So project rectangle projects a rectangle onto an axis and return the min and max projection. So projection is dot corner axis. If projection is less than min, min equals to projection. If projection is bigger than max, and max and min are dot corners 0 with axis. So there is something about normalize and the norm. When we get the corners, we rotate them, we move them. So here we get some vectors that looks like this. Oh, sorry. So we get some vectors that looks like this, and vector that looks like this, and this. And what we try to do, or is it just like this, or do we have the whole width of the... No, it's from the base, so the vectors are larger. We have this instead, this, and this, and this. Kind of. And then for one, we need to get the projection of one vector, and for the other one, we need to get the normalized one. So overlap takes two projections. And if you check if they collide, we get the corners first. We get the axes as well. So get axes for rectangle, corners, get corners of the rectangle. We also get corners here for rectangle. Axes, so edge 1 is vector corners 1.x minus corners 0.x. Compute the axis to test for SAT. Normalize perp edge 1, normalize perp edge 2. Perp is just gets the perp, and normalize, it says the magnitude to it changed the magnitude. So the axes are something we use for... So we're using actually the axis of the rectangle when we project them. Okay. Okay, I will leave this in here and we can continue on this later. I have lost my seniorship. I did lost it, but thank you for support, at least. Bye.